Welcome to another Teachertopian tutorial. We're going to be looking at topic 1, Decomposition and Abstraction, which is 1.1.1 stroke 2 for Edexcel's GCSE Computer Science course. It's right at the beginning. And really, we're at the heart of computer science here, understanding these two terms, decomposition and abstraction. It's part of what we call computational thinking. And computational thinking is where we will be also doing some pattern recognition, algorithmic, let's just say algorithmic thinking, and this would be, let's say, sequence, selection, iteration, so loops. That's at the core of all algorithms. You have sequence steps, different choices that are made, and things that repeat and loop. Those are really at the heart of almost every single program. And then the big two, abstraction and decomposition, right? And decomposition is, the clues in the name, to decompose, right? When you've got compost or something like that, it breaks down into smaller steps. So you can take a big problem and start breaking it down to smaller sub-problems. So you might have, for example, creating the London Underground system's the oldest in the world, isn't it? How would you even start with a problem like that? Creating the first underground system. Well, you might want to then have a team of engineers saying what is the current technology for tracks, and what metals do we have available? Do we have access to all the steel we need? What about the electricity supplies? Have another team deal with power, and another team deal with marketing, and another team deal with the drilling underground, and structural engineers. Yeah, there's all sorts of different sub problems that need to be fixed, and they all work to fit the same thing. I'm just using that analogy because we've got an underground map, and the map itself is a really good example of abstraction, which is another key term here, which is removing any unnecessary detail and just focusing on the most important parts, which makes problems easier to solve. Okay, so is this an exact true representation of what the lines are doing underground? No. But it's been abstracted to a point where the northern line is just a straight black line going up, which is easier to visualize what the function of the northern line is designed to do. In reality, it's probably going to be a bit curvy, go around bends, all sorts of things. But that for the user to have a diagram like this, a mapping, which makes more sense to them about how all of these stations are, the relationship between them, they will need a degree of abstraction from it. So removing unnecessary things that the user doesn't need to know about, and then just focusing on the things that are most important to understand how to get around London. We do the same when we're designing algorithms and we're working with programs. We want to break down a problem into smaller steps, try to solve those, and just focus on the most important things. So in the context of computer science, computational thinking is really involved in algorithm design and how we take a problem, dissect it, and apply algorithmic thinking to it. Now for Edexcel, you'll probably be asked about these two terms. I doubt you'll ever be asked about pattern recognition, even though it's part of computational thinking. And then algorithmic thinking is essentially Python and algorithms themselves. So really it's just these two that we need to look at. So we'll look at some exam questions now, which will help to frame this for us. So let's go. Let's start with a trickier exam question. Explain one benefit of using sub-programs. And this is important because a sub-program is either a function or a procedure. But they are both, in their own right, both decompositions and abstractions. Because we might have a function, let's say length of array, a built-in Python function, right? And that returns the length of, an array. Like, let's say we've got some simple array, okay? And that would return 3, right? 0, 1, and 3 are in the array. We don't need to know exactly what makes this function work, because behind that there's a whole little Python code. Because, let's say we've got a really complicated array that's 1 million integers long, then there's going to be some special sort of algorithmic process there which finds the length of it efficiently. So there's a whole program in itself within Python that we don't really need to know how it works. We just need to call upon it when we need to. So in that sense, it's abstraction, because we're just focusing on the details that we need. Do we have some, do we write some sort of special for loop which checks how many items are in that array? No, we can just call upon the function to do it for us. So that's one of the benefits of subprograms in that sense. It performs the specific tasks that's contained, and you want to use words like so. So you say one thing and then you say another thing, because it's 2 marks, even though it says explain one benefit. So I might say specific task. I'm just abbreviating here. So let's say moved away from main code. I could have, if I need my length of array before I put the main code in there, I can have that above, like my main code. I could have my main code here, and I could have my subprograms all above it in their own kind of thing at the top of the code, at the top of my code, to get what I need out of the way. Subprograms for common tasks are stored in libraries and reused in other programs, again, just like length, so they don't have to be rewritten. And you can use it more than once. I can use this as many times as I like. So just in terms of abstraction, you can describe how subprograms are useful. But there are also decompositions, because I can break my main problem down into smaller subproblems. Like, if one of the things I need to do is find the length of an array, well, by using the subprogram to do that, I've taken care of that side of my algorithm, which has helped to break down the problem into smaller tasks. I've got my main problem, and I break it down into smaller problems, and then I break that down into even smaller problems. So I can add them all up together again, and essentially I've got my solution. So the key takeaway there is, when you've got questions that are 2 markers, you really want to use linking words like so there, so that you can you say something and then it's because of this, or so. A subprogram performs a specific contained task, so it can be moved away from the main code. That's a good way of approaching questions like that. Do not just write explain one benefit of using something, performs a specific task. Like if you did performs a specific task, that's correct. Like, no problem with that. But how are you how's the examiner going to give you the other mark? How is the examiner actually going to give you that second mark? You've got to look carefully at how many marks a question is. All right, let's have a look at another one. Programmers use abstraction to model the real world. Define the term abstraction. Okay, so I think when I was explaining this, I've pretty much given you the answer there. So removing or hiding unnecessary details. So, again, that word, because it's a 2-mark question. Let's say hiding unnecessary details, and just abbreviating here. So, only important points remain. Important points remain. It's the same thing you said, but it's delivered in a way which links 2 clauses there. All right. You've got to have linking words, and so is an easy one to use there. Define the term decomposition. All right, breaking down a problem into smaller steps. And here it's just 1 mark, so they just want you to know what decomposition is. Abstraction's the trickier term there, but I have in my mind the London Underground map. That's a way of using dual coding just to sort of unlock some information for you. Let's have a look at another question here. So this demonstrates the benefit of, really just this question here, the benefit of subprograms is that we can move away from our main code. That's our main program, and we can add our subprogram at the top and move it away from our main code. And we just need to write it once and have this function. Oh, sorry, this is not a function, this is a procedure because it prints a value. It's not returning a value, so we call it a procedure. Define display all in list for index in range of 0 to the length of the list, print index, so that it just print the index of that number and then the item in the list at that index value. So if 0 is cyan, 1 magenta, 2 yellow, 3 black. So anytime we need to do is display all, let's say we've got multiple arrays, then we can just use that same subprogram multiple times and reuse it. So state the data structure used to hold the ink colors. So I'm just going to answer the whole question because I know it does relate to decomposition abstraction later on these other 2 question points, but it is an array because they are all strings, the data types inside. Now a Python list is the closest we have to an array, and an array is defined as a collection of items with the same data type. So it could be integers, floats. Also, they refer to floats as real numbers as well, which can catch you out sometimes. So real numbers, i.e. floats, integers, Boolean values. Now, what's confusing is in Python, a list can contain multiple data types. There's nothing stopping us having like a float here and a Boolean value. We can do that. But in this case, they have all strings in there, so it is an array. But if you put list, they should give you the mark for it because it is technically a Python list as well. So give the contents of index ink colors index 2. So cyan is at index 0, magenta is at index 1, and yellow is at index 2. And state the name of the computational thinking technique used by the subprogram display all to hide the logic of printing. Abstraction. Abstraction is what they're looking for there. I don't quite like the wording of these 2 questions, to be honest with you, because it's potentially a little bit ambiguous. But state the name of the computational thinking technique used when separating logic into different blocks. Okay, so different things. This would be better called decomposition. So if this is decomposition, then that's going to be abstraction. Not greatly worded questions, I don't think, but that's what they're alluding to there. Also, that's pretty small to see, isn't it? But that's how you would answer that. I mean, by using abstraction is looking at removing unnecessary details, potentially moving code away from the main program so you can reuse it. But because display all is a part of our algorithm that we need, it is also decomposition as well, to break a problem down into separate logical parts that we can use to build up the main program. Okay, and it is saying state, so it's one word they're looking for. Good, I think that would be enough for this particular video to give you a sense of computational thinking and how we might. I'll end on one observation, that sometimes students ask why is computer science useful? I'd say, well, it can be applicable to other fields, because when you're doing general problem solving, critical thinking techniques, you can use computational thinking to do that, particularly decomposition and abstraction. When you've got a particularly difficult problem, let's say you're an administrator of a school and it's got nothing to do with computer science, but you have to look at the most important parts of what that problem is, break it down into smaller things. Maybe you give a teacher this task to do, you give another team this task to do, and you can say, look, I've focused on the most important issues here, and let's say it's for exam timetables. The exam's changed. Let's say there's been an emergency bank holiday or something like that, so the plan's out the window. Okay, what's the most important thing? Scheduling, communication with parents. Okay, you deal with communication with parents. You, another team, deal with the scheduling. Another team deal with the printing of the exams, changing the dates. And then you can start to sort of dissect problems into smaller solvable parts, which will help the main thing. And pattern recognition, it might be something that recurs every few years, right? Or something you can anticipate for next time. You say, let me make sure that doesn't happen again. All right, good luck. Bye-bye. If this has been helpful, let me know in the comments.